they told you the differential is dy, which is found by doing f prime of x times dx. Okay, there are different ways of thinking about this. You know, it's not all that different than what we have done before. You know, we called a derivative a dy dx sometimes. So dy dx or f prime, we've said those are the same. If you multiply over this dx, that's where this dy formula comes from. Okay. What it's talking about is the change in our y's. If you look at this picture, okay, the blue line here is my curve. Here is a point on the curve. The pink here is representing a tangent line. Okay? So they're saying if you want to move over some amount, I'm starting here, I'm ending here. So you added some change in x. You took your current x value, you added a change in x. That change in x is the same thing as your dx. Whether you're on the blue or the pink, can we agree that the x value changed the same amount in both of those? Okay. Did the y value change the same in both of those? No. The change in the y on the actual curve is the change in y. But the tangent line is different because I base my tangent line back here. So when I talk about that differential, that's talking about the change in our y from the tangent line approximation. So dy and change in y are not the same thing. So sometimes dy is referred to as like talking about your error. If I were trying to estimate my y value all the way down here, I'm going to have some error involved. And so that's where this idea of dy comes in. So I want to look at an example and see if we can make a little more sense of this. I want to compare the values of change in y and dy. I told you they're not the same thing, so we're going to compare them. If I have this function, x cubed plus x squared minus 2x plus 1, and we're going to do two different times. Part A, my x is going to change from 2 to 2.05. So, what I first need to do, change in y is the actual amount our y changes, so I need the y values for both of these. So if I plug in a 2 to this equation, what do we get out? Nine. If you put in 2, you get 8. I think you missed your x cubed term. So it'd be 8 plus 4 minus 4 plus 1. So if I plug in a 2, I get out 9. What? I just plugged 2.
She put it in square root.
Yeah. In for my head. Are you sure?
Yeah. You said that earlier.
I thought you said 1. That's why. Sorry. Talk louder. Okay, let's plug in 2.01. Oh wait, not 2.01 this time, isn't it? Part A is 2.05, isn't it? Sorry. 2.05 for part A. And we get 9.717625. Okay. So change in y is the actual amount your y's change between these. So you just have to take your y value at 2.05 minus your y value at 2 and see what you increase by. So if I subtract those, my change in y is 0.717625. To find my dy, we need a derivative. No, we know from our previous notation dy dx is the same thing as f prime. So if you do the derivative of this, what do you get? 3x squared. Okay. I'm trying to solve for dy. So if you just multiplied over your dx, dy is 3x squared plus 2x minus 2 times dx. Okay, at the instant we are concerned with x. When I talk about x, I'm talking about your original x value. What was my beginning x value? 2. dx is the amount your x changed. What is my dx? 0.05. It's positive because my x went up 0.05, because I went from 2 to 2.05. Okay, so now you just plug those things in to get your dy. Got 0.7. So the change in y, the actual change in the y value in my function is 0.717625. My dy, which would be the change in y if I were using my tangent line to approximate it, would be 0.7. I want you guys to do B. I want you to find change in y and dy if you're going from 2 to 2.01. So I already know that f of 2 is 9. When you put in 2.01, what do you get out? Okay, so the change in y, all you do is subtract your ending minus your beginning. So it is possible for your change in y to be a negative if your ending y value was smaller. So it's just the ending minus the beginning. So you get 0.140701. Okay, our dy is just your f prime of 2. Or you take your derivative times your change in x. We know that x, our beginning x value is still 2. The dx, what's the change in x this time? 0.01. So if you plug those in for your x and your change in x, what do you get for your dy? 0.1. Okay. Let's see, I just asked you, I think, in the directions to compare these. We can see they're not too far off. Which one is closer, A or B? Which one was closer to each other, the change in y and dy? B was closer, right? These were only off by 0.000701. If you subtract these, they're a little bit further apart. So essentially, kind of like you might expect, the tangent line is a better approximation the closer you are to 2. So the further away from 2 our x gets, the further away from each other the change in y and the dy are going to get. Because the tangent line is really good approximation right there, but the further out you get, the worse it is. Okay, let's look at another one. the radius of a sphere was measured and found to be 21 centimeters with a possible error in measurement of at most 0.05 centimeters. What is the maximum error in using this value of the radius to compute the overall volume of the sphere? So what we found is we had this sphere, we found the radius, but our radius may not be perfect. So if our radius is off by 0.05 of a centimeter, how much is our volume going to be off by? That's really what we're finding here. When we're talking about a sphere, volume of a sphere is 4/3 pi r cubed. We know at the instant we are looking at, our radius is 21. The dr, that's like the change in the radius or the error in our radius. How much is my radius off by? 0.05. So this dx, dy thing, it can also be used, like I mentioned before, as an error approximation. So when I want the maximum error in my volume, what I'm looking for is my dV here. So we know that dV, if you are more comfortable, you can use this notation first and then multiply it over. If I did this derivative, r is my variable, so the 3 comes down, so that makes 4 pi r squared. So dV, the error in volume, is 4 pi r squared dr times the error in my radius. So if we plug in, I'm going to go ahead and multiply out my pi too. So the dV is the error. So the maximum error in the volume is approximately 277 cubic centimeters. Okay, this idea is really important if you think about manufacturing. If you're making parts, you can't just think about every part individually. You have to think about, okay, if this washer is off by 1/10 of an inch, how far off is that going to throw my final product? And so that's essentially what we did here. If my initial radius was off by 0.05 of a centimeter, which doesn't seem like much, that throws my volume off by 277 cubic centimeters. So you can see just a small error in the beginning can turn into a bigger error as you go on. So that's where this idea comes in. Are there any questions there? Okay, so that's the end of section 10. I gave you some of these problems yesterday, so the ones that we are adding to it are 11, 15, 17, 19, 34A, and on 35 it asks you to do several things, but the only thing you're finding on 35, the only thing I want you to do is the maximum errors. So all of this is due tomorrow. We are also at the end of the chapter, so we're going to be getting ready for a test. I know you're going tomorrow, so I'm probably going to go ahead and give you the study guides now too. We have quite a bit of time, that way if you finish these, you'll have your study guide to start working on.